Welcome to Homework Lib.
So in this question, we're given this hydrogen ionide molecule, and we're given a bunch of information about it. And in this question, we want to calculate both its vibrational mode and its rotational mode. So in part A, we want to first start calculating its rotational mode. And we want to find the moment of inertia of it. So in order to find the moment of inertia is given by reduced mass times r squared. So we have to first calculate the reduced mass of this molecule. So the reduced mass, mR, equals mass of hydrogen times mass of ionide divided by mass of hydrogen plus mass of ionide. So this is 1.67 times 10 to the negative 27 kilogram times ionide is 2.11 times 10 to the negative 25 kilogram over 1.67 times 10 to the negative 27 plus 2.11 times 10 to the negative 25 kilogram. And we see this gives us 1.657 times 10 to the negative 27 kilogram. And with that information, we can calculate the moment of inertia, which is just the reduced mass times the separation, which is 0.16 nanometer. This gives us 4.24 times 10 to the negative 47 kilogram meter squared. So now let's look at part B. Part B asks us to look at the energy involved in several different transitions. So for number 1, we have the transition from n equals 1, L equals 1 to n equals 0, L equals 1. Part 2, we have n equals 1, L equals 2 to n equals 0, L equals 1. So both rotational and vibrational energy underwent a lower transition. Finally, we have n equals 2, L equals 2 to n equals 1, L equals 3. Okay, so let's look at the first one. The first one is the simpler case. In this case, we only have the vibrational energy that goes down by one level. So the vibrational energy is given by vibrational energy En is n plus 1/2 h bar k prime over m. Here we do not know what k prime over m is, but this is k prime over m is just omega. So it might be more helpful to write it as h bar omega. And we do not know what omega is, but we know what frequency is. And frequency, h bar omega, so omega equals 2 pi times frequency, and h bar equals h over 2 pi. So it is easier to rewrite this equation as En equals n plus 1/2 h. So this gives us the vibrational energy of all those systems. Okay, and now let's look at number 1. Number 1, we have the vibrational energy decrease by one level. So the change of E, delta E, is 1, 2, 0. Let's see. Okay, yeah, sorry, a quick mistake. Number 1, we actually have both levels decreased by 1. So the amount decreased by the vibrational energy, delta E, is h bar times F. So this is how much the vibrational energy decreases. And then let's look at the rotational energy. Rotational energy is given by L times L plus 1 h bar squared over 2I. And we already calculated I in the previous question in part A, so now we can just use the result. So when it decreases again, we also need to add L times L plus 1 h bar over 2I. When it's at L equals 1, this number is equal to 2 times h bar over 2I. When L equals 0, EL equals 0. So this is a total amount of energy that changes is h bar over h bar squared over I plus hf. And finally, we want to find the wavelengths associated with the photons that was emitted in this process. And the wavelength is given by lambda equals hc over delta E. Okay, so let's get a new page so we can write more clearly. L equals 1, N equals 1, 2, L equals 0, N equals 0. We have change of rotational energy is HF. Change of vibrational energy is HF. Change of rotational energy is h bar squared over I. So the total change of energy is added together, and the wavelength photon is hc over delta E equals hc over h bar squared over I plus hf. So this is the equation for this question. And if we are given h bar and h are constant, I we found in the previous question, and if I plug in all the numbers, we will get a wavelength of 4.30 micrometer. So this is the first question. The second question, we have n equals 1, L equals 2, n equals 0, L equals 1. So in this case, most things are the same. We still have n equals 1 to n equals 0, so the vibrational energy is the same. It's still HF, but the rotational energy is different. In L equals 2, we have 2 times 3 times h bar squared over 2I. Well, in L equals 1, we have 1 times 2 h bar squared over 2I. So if we subtract them, we'll see that now the difference in rotational energy is to be 2 times h bar over I instead of just h bar over I. So the wavelength will be a little bit smaller. It will be 4.28 micrometer. So finally, for part 3, now we have vibrational energy goes down by 1, but rotational energy increased by 1. So now it's lambda hc over delta E. Rotational energy from 2 to 3, so it was actually a negative value. So when L equals 2, we have 2 times 3 equals 6 times h bar squared over 2I. And when it's 3, we have 12 times h bar over 2I. So we have negative 3 h bar squared over 2I over I. And then the change of vibrational energy is still HF. So this one, when we calculate it, it is a very small energy difference actually because they cancel each other. And the final wavelength is 4.4 micrometer.